Dushanth Seevaratnam. I'm a postdoc researcher here at the University of Cambridge, specifically Department of Chemical Engineering. And I've been involved in the AfriDx project mainly as like a protein engineer and helping some of our collaborators troubleshoot with regards to use of the protein with their systems. So a lot of my work has been on the protein engineering front. So the idea is there's a lot of overhead costs labs can experience when it comes to purchasing the enzymes. And so the idea is, can you actually just locally produce these enzymes? It's not, sometimes it can be as straightforward as just essentially taking the genetic sequence for the enzyme and putting in plasmid. But then when you kind of think about the downstream processing of it, there's still a lot of expenses there. And so the idea is, can we modify those proteins so that we reduce the cost of the downstream process, either through cheaper materials, faster processes, or even have to like do less cleaning, which is sometimes kind of nice. And then essentially trying to figure out what's the right combo, and then optimizing the system to essentially maximize performance using these locally produced enzymes. The obvious one, of course, is cost, right? Rather than having to import in diagnostic tools, the ability to produce your own diagnostic tool would dramatically reduce the overall cost that you would experience. The other bit is mainly production and availability. I mean, here in the UK, at some point, we had shortages on lateral flow tests. I'm from Canada, and I think during like the height of the pandemic, maybe if you're lucky, you could get access to 2 or 3 lateral flow tests over the course of 5 months. And so if you're actually producing it locally, then that hopefully would reduce that burden. You're not waiting for things to be shipped in. I mean, even in Canada, we're waiting for lateral flow tests to come in from the States. And if they didn't provide it, then we didn't get any, because we have actually no production up there. So yeah, LAMP has been around for about 22 years at this point. And the RT version came about 4 or 5 years after that. And it's one of the difficulties with LAMP is that it is, it's prone to false positives. And so there's a lot of effort and troubleshooting that needs to go in to actually figuring out how do you get the maximum amount of sensitivity and maximum performance while minimizing false positives. And it's one of those things where there is some need for expertise in it, and oftentimes we kind of convert PCR just into the LAMP in terms of methodology, and it's not quite the same. There's a lot of initial processing we need for the primers themselves. But the really cool thing about LAMP is if you can figure out that combo, the right combo of 6 primers that don't produce false positives, you can get essentially activity in under 30 minutes. You can do a variety of non-gel or non-instrument-based diagnostics. One of the common ones is just a color change from a pH, right? So you can have the sample go from red to yellow or green to blue and so on and so forth. And it's just, it's nice to actually have something which you just have to heat up at a single temperature, which also reduces cost, and simply look for a color change. And so it's one of those things where someone might need some training for how do you essentially process or deal with a human sample. But in general, once you have that training to actually run the LAMP reaction, doesn't require as much training as your traditional PCR tests, and is also proven to be almost as sensitive, if not more sensitive, than some of the PCR tests available. I think one of the initial papers that came up for LAMP mentioned how you could easily generate about 10 billion copies in less than 40 minutes, which is a crazy amount of target DNA. So one of the really cool things about RT-LAMP is the fact that we're targeting RNA specifically. And so, of course, COVID is an RNA-based virus, and that's why it's compatible. But there's a lot of other RNA viruses out there. So one of the big examples I often hear, and some of my family actually in Malaysia always tells me, being like, this is nice, but could you make a diagnostics for dengue? And so dengue is one of those big ones that are out there, and it would be nice to sort of work with that. And then there's also some work with regards to the use of essentially this RNA technology to track various mRNA production within people, because those can be markers for cancers and a variety of other diseases, ranging from like liver failure to infectious diseases as well.